Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. Today's speaker is Dr. Fan Lee. Dr. Lee is an assistant professor in the Department of Biostatistics at Yale School of Public Health. He's also a faculty member in Yale's Center for Methods in Implementation and Prevention Science and at the Yale Center for Analytical Sciences. His main research interests include methods for designing and analyzing pragmatic cluster randomized trials, causal inference for randomized trials and observational studies, and techniques for improving internal and external validity for treatment comparisons under different study designs. Dr. Lee is the principal investigator of a Patient-Centered Outcomes Research Institute funded award investigating new study planning methods and software for testing treatment effect heterogeneity in cluster randomized trials. In addition, his research has been supported by several other PCORI and NIH-funded awards. Dr. Lee is an active member of the Biostatistics and Study Design Core of the NIH Pragmatic Trials Collaboratory and executive committee member of the Design and Statistics Core at the National Institute on Aging Embedded Pragmatic Alzheimer's Disease and AD-related Dementias Collaboratory, also known as the IMPACT Collaboratory. Dr. Lee also serves as an associate editor for Statistics in Medicine, for clinical trials, for implementation science, and for epidemiologic methods. It is my very great pleasure to welcome Dr. Lee.
Thank you, Dr. Murray, for your invitation and kind introduction. It's actually my greatest honor to come back to the seminar series for a second time and share my perspectives on cluster randomized trials. Today I've got a very ambitious title toward causal influence in cluster randomized trials, Estimands, and some reflection on current practice. I won't have time to be very exhaustive because there are so many to cover under this very general topic, but my intention was to try to stimulate the start of a conversation so we can offer more clarity toward what we do with these trials that are becoming more popular these days. And to start with, cluster randomized trials are going to have been a consistent theme of this webinar series. And as many of us may know, these trials refer to studies where we randomize entire clusters or groups of individuals to treatment conditions. And a cluster can be a hospital, a school, a village, or a work site. And they're often conducted when the intervention is naturally implemented in the cluster level or to avoid contamination of treatment within clusters. Typically, in the absence of non-compliance, individuals receive the same treatment within the same cluster under the cluster randomization scheme. These trials are also increasingly popular in pragmatic trials, at least in the US and I'm sure across the world. An incomplete survey that we have done within the NIH Pragmatic Trials Collaboratory suggests that among the 22 demonstration projects that were supported in this collaboratory, there are 16 cluster randomized trials and only 4 individually randomized group treatment trials. These are partially nested designs where there is a treatment-induced clustering and only 2 traditional individually randomized trials. And so suggesting the cluster randomization is popular. To guide the practice of these cluster randomized trials, there are multiple textbooks that are classics, and they all deliver a consistent message that is the design and analysis of these trials must account for the inter-cluster correlation coefficient, or ICC, of the outcomes in some fashion. In the analysis of cluster randomized trials, a primary interest is to estimate the treatment effect or intervention effect. Despite cluster level randomization, the outcomes are frequently collected at the individual level, even though they can be summarized at the cluster level. In this context, with multi-level data, the linear mixed effects model and generalized estimating equations, or GE, are two mainstream multi-level regression model tools. And we often take the coefficient of the treatment variable, the betas, and interpret that as the average treatment effect or average intervention effect. While this is a common practice, a potential challenge in interpretation of that beta parameter is that this treatment effect estimand or contrast is defined based on a specific model, and that may change with the link function specification, the covariate specification, as well as the random effects specification under linear mixed effects model or generalized linear mixed effects model. And if the model we postulate is actually not the underlying data generating process, which often is the case, then it is a little unclear what that treatment coefficient refers to and what contrast are we talking about under potentially misspecified models. And because of that level of ambiguity, there is an increasing interest in defining estimands at the outset. And this is actually taking off in individually randomized trials, thanks to the estimand framework that's been getting really popular in the past few years. In its definition, the estimand or a causal estimand is a precise description of the treatment effect investigators wish to estimate from a study, and can comprise 5 aspects, including the population of interest, the treatment conditions that we are interested in comparing, the endpoint of interest, the summary measure, whether we are talking about a risk difference, a difference in means, a risk ratio, or a odds ratio, as well as how intercurrent events are to be handled. And although a little bit more unfamiliar to us maybe, the intercurrent events refer to the events that happen post-randomization that may affect or prevent the occurrence of the final outcome of interest, such as treatment discontinuation, switching, and death before the final outcome is observed. Taking this concept into consideration, it is actually a little unclear how the current practice with interpreting the regression coefficients in cluster randomized trials fully address each of these 5 aspects. And in this talk, even though we won't be exhaustive in all of these aspects, we want to offer some clarity on the aspect of the population in discussing estimands for cluster randomized trials, as we will illustrate soon below. A central question to ask in this context in defining estimands with multi-level data is, what is the population we are trying to average over? And to illustrate that consideration, we consider a hypothetical cluster randomized trials with 6 clusters. Very simple, simplified example, where we have half of the clusters with only a small cluster size of 10 individuals in that cluster, but with a relatively larger causal effect within those clusters equals to 5. And the remaining clusters are going to be larger clusters with 100 individuals per cluster, but with a relatively smaller causal effect equals to 1. In this table, which we pretend we know everything as the truth, we can define a treatment effect as an average across all individuals in the study. And if we do the algebra, that gives us back 1.4 as a treatment effect summary. However, if we define the treatment effect as an average across clusters in the particular study and try to average the right column, basically, we get 3 as our summary of the intervention effect. And it's almost a 2-fold from the previous summary. And this difference can be substantial, actually, depending on how the treatment effect within cluster can co-vary according to the cluster size variation, as depicted in this hypothetical example. To see this issue a little bit more clear, we could try to even formalize the estimand as a concept under the so-called counterfactual outcome framework, where we define Yij1 and Yij0 to be the 2 counterfactual outcomes for each individual J in a cluster I that correspond to what's going to happen in terms of the outcome if the cluster this individual belongs to is randomized to intervention or usual care, possibly contrary to the fact. And we write Ni as the number of individuals per cluster. Based on this definition, we could write out the individual average treatment effect, the individual ATE in this first equation as the average over the individual level contrast of the counterfactual outcomes across the entire cluster individual population, given by the first equation. And in addition, we can also define the cluster average treatment effect, the cluster ATE, as an average over the cluster specific average effect, which is further defined as the average of the within cluster counterfactual outcome contrast across the individuals in that cluster. So there is a double average in this second definition of the average effect estimate. There is an emerging literature that's been very recent that tries to characterize or offer some clarity on these two types of estimates, which I gave in the slide, under potentially different perspectives, either a finite population perspective or an infinite population perspective, where we sample the clusters from a population of clusters. The nuances of these two frameworks are irrelevant of this talk, but we do give the expressions in the slide. And there's a one-to-one correspondence, basically, so they can be interpreted very similarly. In this talk, we'll focus on the difference or absolute scale, but we can extend the estimates to ratio scales. Basically, using the same counterfactual outcome notation, we could try to, if we have a binary potential outcome, we could try to summarize the population incidence in terms of the individual level summary or the cluster level summary, and then apply the risk ratio or odds ratio formula to define the estimates, very similar to the previous slide where we focus on the absolute scale. So what does this possible estimate actually mean, right? We have two versions of that. The individual ATE tries to answer a question of what is the expected change in the outcome associated with the treatment for a typical patient. For instance, for an intervention delivered to patients aiming to reduce mortality, then the individual ATE may be of interest, as this represents the population impact of switching from control to intervention. The cluster ATE tries to answer the question of what is expected change in the outcome associated with the treatment for a typical provider or clinic as a cluster, as well as its natural patient population or patient panel. For instance, in a trial aiming to reduce unnecessary prescribing of antibiotics to patients in which doctors act as a cluster, then a cluster ATE may also be of interest, as this clarifies the intervention's effect on clinicians' prescribing habits. And of course, there can be situations where these two estimates are both of interest, and they're not actually mutually exclusive. The central question then drives the presentation forward is that when will these estimates differ, right? When will we need to tell the difference between them or tell apart them? And as alluded to by the previous example, the key factor that drives such difference in the estimates is whether the cluster size is actually informative. There are two types of informative cluster size. In the first type, the outcomes are different, or the outcome distributions can be different between small and large clusters, but treatment effect remains the same. For instance, the baseline event rate can be 10% or 20% in small and large clusters, but the odds ratio is constant across clusters to be 0.75. Under the second type of informative cluster size, the treatment effect can differ between small and large clusters, or the cluster size appears as an effect modifier. For instance, the odds ratio is 0.75 and 0.5 in small and large clusters, regardless of the baseline event rate. And to what extent these two types of informative cluster size can lead to differences in the two estimates we have defined earlier can depend on the effect measure. For instance, we have explained that carefully in this paper referenced published in International Journal of Epidemiology, where we basically said that if you have a collapsible effect measure, maybe the second type is more critical, But if you have a non-collapsible effect measure, both types of informative cluster size may be factors leading to differences in the two estimates of interest. The informative cluster size can occur, for instances, when there are differences in staff experiences or levels of care between larger and smaller hospitals, which eventually will lead to changes in the outcomes or the intervention effect, or because of differences in the socioeconomic status between larger urban schools and compared to smaller rural schools of the participants that may lead to differences in the final outcome of interest. And so just to summarize, these can occur when factors that differ between small and large clusters can also affect the potential outcome or counterfactual outcome or interact with the intervention group or intervention condition. So when we pin down the estimand, there can be interest to try to use the estimand, try to pick the estimators to target the estimand of interest. And so for that, we try to provide a recipe for estimand aligned analysis. The key message here is to realize that the individual ATE and the cluster ATE basically give equal weight to different components. For instance, the individual ATE gives equal weight to each individual. And therefore, if we pursue a cluster level analysis with a cluster level summary statistic, we should analyze the cluster level summaries using a weighted regression with weights equal to the cluster size. To reflect, we give equal weight to each individual. And if we pursue an individual level analysis, we could use the generalized estimating equation with a working independence assumption to give equal weight to each individual. In contrast, for the cluster ATE that gives equal weight to each cluster, the analysis of the cluster level summaries could just proceed with an unweighted regression model where we do give equal weight to each cluster. But if we pursue an individual level analysis, we could consider a generalized estimating equation with a working independence assumption, but with inverse cluster size weight, 1 over Ni, to give back equal weight to each cluster in the presence of variable cluster sizes. And of course, all of the recipe here are simple recipes of unadjusting for covariates. If we want to adjust for covariates, there's a very elegant generalization in this reference provided in the last line of the slide. So in practice, even though before we review this recipe, there are occasions where we actually face different decisions for choosing models. And that decision, more often than not, is not based on estimand, could be based on efficiency or other considerations. And for instance, we take the generalized estimating equation as a simple example, again, without covariates. We might be facing the choice of deciding on a working correlation matrix where we can choose the independence working correlation or an exchangeable working correlation, which actually models the intra-class correlation coefficient in these trials. We could adopt the inverse cluster size weighting to remove extreme influence on the large clusters, or we don't do anything. And that can lead us to 4 variations of the generalized estimating equations analysis given by this table. If we have no informative cluster size, for instance, this can be the case where the intervention effect is constant across clusters, regardless of how variable the cluster sizes are, as given by scenario 1 and 2 in this figure, it's completely fine whatever approach we use and whatever decisions we make, because in this particular case, the estimands, the cluster level ATE and the individual ATE basically will coincide, and all of these 4 estimators will converge to the single target that's well defined. However, if we're in a situation where the cluster size is indeed informative, so there can be an association of the cluster size variation to the potential outcome contrast in a cluster, then we get into trouble, because the target, the limit of these 4 types of analysis can all be different. And only 2 of them, the independence estimating equation and the independence estimating equation with inverse cluster size weight, can target the cluster level ATE and the individual ATE that are well defined in the aforementioned slides. And the other approaches with an exchangeable working correlation structure or the inverse cluster size with the working exchangeable correlation structure can be deviating from the estimates we define at the outset. And in particular, in this case, if we combine the inverse cluster size weight and the working exchangeable working correlation structure, we get into a situation where two weights make a wrong, and the limit of the target of that estimator can be actually farther away from the individual ATE or cluster ATE. So just to give a little bit more clarity, if we actually study the probability limit of the treatment coefficient estimator under this identity link function, generalized estimating equations set up adjusting for only the treatment indicator, we can tabulate the limit expression of these four types of estimators under the counterfactual outcome framework. And we immediately realize that the first two approaches are targeting the individual ATE and the cluster ATE without any ambiguity and can handle the informative cluster size. But the latter two options will get you into trouble, because if you have cluster size that are informative, then the limit will depend on this rho star parameter that is the limit of an ICC estimator under these models, reflecting the choice of the non-independence working correlation. In this case, if we try to weight by a non-independence working correlation, this precision weight can try to introduce bias if the cluster size is correlated with the treatment contrast within each cluster. However, as we've shown in the previous two figures on the left-hand side, if we don't have this issue, if the effective treatment actually is constant, happens to be constant, and does not depend on the cluster size, then we're okay, because these approaches will target the same limit. And that's exactly the case where a non-independence working correlation can offer you an efficiency gain and might be better. To operationalize this types of estimate-driven consideration, we want to offer a simple example that's been written in the IJE paper, where the context is a cluster randomized trial comparing a quality improvement, a QI intervention to improve outcomes in patients undergoing emergency laparotomy, where the intervention is implementing a hospital-wide improvement program in each cluster. The primary outcome is mortality within 90 days, and the secondary outcome is whether a senior surgeon is present in the operating room performing the surgery or supervising a junior surgeon in doing so, which is intended to measure success of the QI intervention in changing hospital practice. For the primary outcome, the interest lies in effect on individual patients, where the question can be framed as how many additional lives can be saved through this QI intervention. In this case, we might argue that the individual ATE might be of relevance. For the secondary outcome, the interest might lie in measuring treatment success in changing hospital practice, with the question being framed as whether the QI intervention can improve the quality of healthcare delivery for an average hospital. And in this case, we might argue the cluster ATE appears to be more relevant. And of course, there is no uniform solution to all trials, and require a very careful conversation between statistician and the study team to really reflect on the scientific goal of the study. And so here is only a simplified example, and it could be well the case that both estimates are important, and we need to address both. Once we pin down the estimates, it would be ideal to try to think through the statistical decisions to target these estimates that are clearly defined. And suppose there is concern that the impact of treatment on outcome can differ between smaller and larger clusters because of differing level of resources and available across different clusters. In this case, we cannot rule out informative cluster size, and we may end up in a situation as our hypothetical example. And suppose we want to perform an analysis without covariates, and we wish to estimate the risk difference on the absolute scale for the primary outcome on mortality, where the interest lies in the individual ATE, we could use independence generalized estimating equation with the linear link function. For the secondary outcome on the senior surgeon presence, we could consider the independence generalized estimating equation plus the inverse cluster size weight, as we specified in the recipe, to estimate the cluster ATE. And again, of course, it's only a simplified discussion for the unadjusted analysis to really illustrate how we can perform, how we can operationalize the estimate aligned considerations by pinning down estimate before coming up with statistical solutions. Despite the rigor of the counterfactual outcome framework we have laid down, it seems to actually raise more questions than offering answers to many questions we may have in mind, especially we connect with the current practice, because we may not be always doing so in what we do with our cluster randomized trials collaborations. And there are several questions that may be worth mentioning. The first one is when or to what extent the informed cluster size is an issue. And just to try to offer more clarity here, the informed cluster size concerns the marginal correlation between the cluster size and the potential outcomes in a cluster. And the covariates are a little bit irrelevant here unless we define Estimands conditioning on covariates. We could imagine the covariates to be explaining away variations due to the cluster size, but that doesn't change the fact that these two Estimands may differ. The second question is that in the recipe we outlined in the table, we have not really placed linear mixed model or exchangeable GE in that recipe, but we have been using that for decades. So are we doing things wrong for decades? How do we try to give a counterfactual interpretation, or when do these models have a counterfactual interpretation for estimating some sort of average causal effect? And finally, are the methods in table 1 the only methods for estimate align analysis? Do we have more to offer? And so we have some answers for parallel to arm randomized cluster randomized trials, but not to all designs, because we have a lot of complexity if we branch out to other types of study designs. The first question of when cluster size can be informative and is an issue in practice, that needs more empirical evidence for sure. And there is really no uniform answer. And I want to mention that there is ongoing work led by Brandon Kahan, who is an expert in Estimands and led the work in IJE that I have just presented, and his ongoing work with reanalysis of some studies will provide some clarities on when this could be an issue. The second question of multi-level regression models adjusting for clustering in the model fitting process. I will explain in a minute that under some structural conditions we impose that are not really parametric modeling assumptions, these models can be model robust for estimating a common average causal effect. And that's going to be the focus of the next part of this discussion. And finally, the methods in table 1, the recipe, is not the only methods. We can always do better by leveraging covariates, or there could be other estimators that require us to study that can offer estimate align analysis without with adjusting for factors we want to control for, but without really obscuring the clarity of the estimates. And so to move on, we want to look at a specific candidate analysis model not mentioned in table 1, the linear mixed model, to address the second question we have just laid out. The reason why we focus on this approach is because it's by far the most commonly used approach in analyzing cluster randomized trials with a continuous outcome, for instance. And actually, it is the basis of many development in the biostatistics literature for designing cluster randomized trials. So it really has a long history. The question is that, is linear mixed model estimating a valid average causal effect, right? Do we have a counterfactual interpretation of this model under some conditions? And we want to demystify the structural assumptions that we need for achieving causal inference with a clear estimate under these models to offer some ideas on what we have been implicitly, we may have been implicitly assuming in our daily practice. To proceed, we start by conceptualizing a cluster randomized trial with I clusters, each of which includes n star individuals in its source population. And so we are making this assumption of an equal number of individuals in the source population in each cluster as a technical consideration to facilitate the discussion, but can be relaxed. It could be relaxed. It's a seemingly strong assumption, but when the source population varies in size, we could imagine a representative within cluster population of size n star to equalize the source population somehow. And we assume that what we observe, which is ni individuals, are going to be a sample from that source population. And the treatment is assigned at the cluster level with ai equals to 1 if the cluster I is treated and 0 otherwise. For every individual in my source population, we define Yij as the observed, potentially observed outcome. And under the consistency assumption, which is often invoked under this framework, we can link the observed outcome to the counterfactual outcome, depending on whether the cluster that individual belongs to receives intervention or usual care. And we write xij as a p-dimensional vector that we measured at baseline, including individual demographics and other clinical information, and uij to be a list of the unmeasured covariates. So the structural assumption one that we need is a population sampling assumption, where we try to write down the complete data vector for each individual j in a cluster I as this wij vector, consisting of the pair of the counterfactual outcome for that individual, as well as the covariate information that are either measured or unmeasured. And we can define a complete data vector of the cluster I by appending these individual level information across the clusters in the source population. What we assume is that the cluster-specific data vector wi is a random draw from a population of clusters. And then within each cluster, the element wij for each individual follows a common marginal distribution. In other words, the element in this wi vector are going to be marginally identically distributed, but the elements themselves can be arbitrarily correlated. What this assumption assumes is that it doesn't really assume a homogeneous effective treatment across clusters. It can allow for random intervention effect or cluster covariate dependent intervention effect, as long as we have a common marginal distribution by averaging over these sources variations. In addition, the conditional correlation structure within clusters can vary among individuals. So we are not really assuming one type of correlation structure for the cluster population. So this assumption basically offers that level of flexibility. In addition, we need another structural assumption, that is the random within cluster sampling that links between the observed cluster population to the underlying source population. And if we denote mi as a collection of the sampling indicator of everybody in my source population, with 1 equals to be sampled in my study and 0 not, we assume that these sampling indicator that we have are going to be independent and identically realizations of a common population distribution. And the distributions of the sampling process is independent of the potential outcomes, treatment, and measured or unmeasured covariates. And basically, it assumes that within each cluster, the enrollment or sampling of individuals, as well as the cluster size n, is random and independent of the remaining data information. And of course, this can be violated if we have informative enrollment that depends on the treatment conditions or depending on other covariates, in which case we might be in a situation with selection bias that happens post-randomization. And there's a different literature that addresses this issue, and we will not go into that, but only offer the citations here. Under the setup that's relatively nice and ideal, we actually have been ruling out informative cluster size, which happens to be what we often assume in practice with cluster randomized trials. And it is precisely this condition, these conditions that really allow the individual average and cluster average causal estimand to coincide. And so if we write out the individual ATE and cluster ATE as we have done in the previous slide, under the aforementioned structural assumptions 1 and 2, we can apply a population level expectation on these two estimands, and that will give us a common average causal effect estimand that can be interpreted in two ways. It could be a cluster ATE or an individual ATE, and we can define that based on the underlying source population, where we basically apply an individual level expectation on the individual level contrast given by this last equation. And with that in mind, as our target estimand, we can talk about the estimator. And one of the estimates we oftentimes fit, and we studied a lot in the literature for cluster randomized trials, is the linear mixed analysis of covariance models, or linear mixed and Causal models, where we relate the observed outcome Yij to a common intercept, beta 0, a treatment effect beta A times the treatment indicator AI, as well as covariates we might want to adjust for to control for imbalances or to improve efficiency, and a random cluster level intercept delta I and a random error epsilon ij, which are assumed to be normally distributed. And in this construction, we have the ICC defined as the ratio between the variance component of the random intercept over the total variance component. And we consider maximum likelihood estimation of these model parameters in this model based only on the observed data that we have based on the enrolled or observed population, so NI individuals in each cluster I, and we denote hat by the estimators that we obtain under this framework. If we want to pursue a model without covariates, we could remove Xij in this model, and the results we show below still apply. And frequently, we interpret beta A from this model as the treatment effect on the absolute or difference scale, and we use the model-based variance estimator for generating p-values and confidence intervals, basically for conducting statistical inference. There are two interesting results that we want to share, one of which is that if we assume the aforementioned structural assumptions 1 and 2, the linear mixed ANCOVA model estimator beta A hat is actually consistent for estimating the common ATE on my source population we have just defined, even if the model is misspecified. And the takeaway is that the point estimator for the intervention coefficient is always correct, almost always correct, as long as the structural assumptions hold. Even if the functional form of the covariates are incorrectly specified, the random intercept assumption is incorrect and or the residual normality condition is violated. And what's perhaps more interesting is that if we have a one-to-one balanced allocation, the model-based variance based on the Fisher information converges in probability to the true asymptotic variance of the ATE estimator from the linear mixed ANCOVA model, with the takeaway being, as long as the structural assumption hold and we have a balanced allocation, we can trust the standard error estimate and p-value from the standard software output, even if the linear mixed ANCOVA model is not fully correctly specified. The caveat, however, is that if we have an unbalanced allocation, the model-based variance estimator is no longer guaranteed to be valid, and we might want to use the robust image variance to fix that, which can be obtained in many softwares as well. To convince us that this is indeed the case, we have done some simulations to validate and just to show us that under these structural assumptions, which include many types of data generating process, we could get robust inference of the ATE that's well defined under the aforementioned assumptions. And we consider in this demonstration two types of data generating processes. The first one is we have a constant intervention effect across the clusters for everybody. So there's only a true main effect of the treatment, but we have a very complex functional form of the covariates, including higher order terms, as well as potential covariate interference, where the potential outcome of this individual can depend on the covariates of others in the cluster, just to complicate the process. But we maintain the normal random assumption, the normal assumption of the random intercept and the residual in this model. In the second data generating process, we assume individual level effect modification. So everybody will have a different individual level causal effect depending on their covariates. And so the individual level contrast Yij1 minus Yij0 is a function of the covariates. And in addition to that, we assume a random cluster level coefficient that allows the effect to be different across clusters. And in addition, we try to challenge the model by even making the random effects and the residual error terms to be non-normal in this case. But in the analysis of the data we generated, we always fit the linear mixed ANCOVA model we are familiar with, where we only include a linear term of the covariates as well as a random normal intercept and a random normal residual error, either with or without the covariates. And we compare several metrics, including bias, standard error of the coefficient estimators, as well as the coverage, as well as the relative efficiency between the adjusted versus unadjusted models. And a consistent finding is that asymptotically, the linear mixed and Causal model, even if they're not fully correctly specified according to the true data generating process, are relatively unbiased. And the bias is very small for targeting that common ATE estimate. And since we assume a one-to-one randomization, it's a balanced design. We can also trust the model-based variance estimate. And that's why the coverage probability is consistently around the nominal level, 95%. The relative efficiency of the adjusted linear mixed model controlling for linear Xij can be sometimes more efficient than the unadjusted version. And that level of potential improvement in efficiency can depend on actually the underlying data generating process, because we don't always have a fully correctly specified model. And so that's not always guaranteed. So the robustness of the linear mixed analysis, the linear mixed and Causal models actually was demonstrated earlier in the literature for cluster randomized trials, even though that's only through simulations. For instance, there's a paper published by Dr. Murray in 2006, about 15 years ago, that demonstrated if we fit this model to data generated under non-normal random effects and non-normal residual errors, we can actually get the correct type 1 error rate. So that's very similar in spirit to what we are saying here. It's only just we provide a formal justification mathematically by pinning down the estimates and the assumptions needed for valid inference, and to provide a green light to use the model-based variance under an equal allocation scheme. And in this perspective, linear mixed and Causal models applied to CRTs is actually more robust than we originally thought. We cannot formally prove the results under restricted maximum likelihood, but we have done some simulations to show that there is really no difference under, even though the proof is done under maximum likelihood estimation. I want to also mention that this work on model robustness from the linear mixed and Causal model is an elegant parallel to some results developed earlier for linear regression and Causal models under individually randomized trials in the absence of the multi-level structure. So this whole discussion can also be extended to stratified randomization, where we can consider a situation where we want to control for some imbalances in the design stage. We can pick one important variable which we want to stratify on, and we assume we have a fixed number of strata, and we assume the randomization proportion within the strata remains constant. Sometimes it's not feasible in small number of clusters, but we assume that's the case asymptotically. In this case, as long as we adjust for a stratified variable as I in the model, we can still have the same findings as we have shown previously for unstratified randomization, that the point estimate is going to be correct even if the model is incorrectly specified. The model-based variance under equal allocation is going to be correct even if the model is incorrectly specified. And the benefit of stratified randomization is that you could possibly get a smaller variance than the unstratified randomization, even if the model you fit is incorrectly specified. And so we've presented a suite of considerations for Estimands and analysis models for cluster randomized trials with maybe two consistent and strong messages. I want to summarize that to wrap up the discussion. The first message being that in practice, if informative cluster size arises and can be a consideration and can be of concern, then the individual ATE and the cluster ATE answers different questions in cluster randomized trials and can be different in magnitude. And this issue of Estimands was actually interestingly noted back in 2000 in that classic book by Donna and Clark on page 13 of the book, which basically says that the target of inference in CRTs can be either at the individual level or community level, even though they didn't really formalize the estimand concept in the book. And from this perspective, estimand should really drive the analysis, but not vice versa. And we should think harder through estimates and potential for informative cluster size. If that's a concern, we could even consider doing the analysis multiple ways to really see potential empirical evidence of how the results may differ if we target different estimands, or they're going to be the same. Of course, we don't have a formal approach to assess cluster size variation that are informative in this context, but that could be an open question to address in future studies. The second message is that we want to really find out and demystify the structural assumptions that we need to generate causal inference under linear mixed models, for instance. That's basically going to be the non-informative cluster size, first of all, and random enrollment or random sampling within the clusters, in which case, not only we can trust the linear mixed effects model, but also the two estimands we defined earlier coincide. And it is precisely this case where the standard linear mixed model is consistent, and we can trust the model-based variance under equal allocation. But we have to realize that there are structural assumptions we implicitly make, but we rarely acknowledge. And so I offer this very simple tree diagram to ask the question of whether in a real CRT, do we believe or do we consider the structural assumptions to be plausible? And if so, then we could consider the linear mixed and Causal model with only adjusting for covariates. And that could always be correct for estimating the common AT estimate. And the model-based variance is correct under equal allocation. But if not, then the linear mixed and Causal model may be wrong, and because it could target an ambiguous estimate. In that case, we might want to follow the recipe of table 1 to figure out what we want to target in terms of the analysis method we consider in the analysis. And as a final word, I want to say that the standard linear mixed model is very robust to assumptions on modeling aspects, but we really require the structural assumptions that we need to be aware of. And it is precisely the lack of those structural conditions that can lead to differences in a causal estimate in this multi-level context. To wrap up, I want to mention that this talk is primarily based on 3 papers. The first one is led by Brennan Kahan, who's an expert in Estimands, and has led the paper on Estimands to demystify this issue in this multi-level context and the cluster size variation that could be informative. And it's published early this year in International Journal of Epidemiology. The second paper is a product led by Shuqi Wen, who is now a postdoc at Yale and has been working with investigators in the NIH Pragmatic Trials Collaboratory, and the paper has been published in Contemporary Clinical Trials early this year. The second part of this talk is based on a paper that's on arXiv, led by Bingkai Wen, who's an expert in model-based inference of randomized trials, and is really the brain behind this development to provide elegant results on the linear mixed and Causal model. This work is partially supported by 2 PCORI contracts, one awarded to me and one to my Penn collaborator, Dr. Michael Harhay. And I'm grateful for 2 collaboratory support on my research in cluster randomized trials. I want to also extend my thank you to my collaborators who have been helping me and commenting on the slides. I think I am running out of time. That's it.
Thank you, Dr. Lee, very much. A terrific presentation. We've got time for some questions, so let me get started with those. You've noted that the individual, or I would note that the individual average treatment effect is influenced more by large clusters, at least potentially, than by small clusters. And does that mean we should always use the cluster average treatment effect when there's considerable variation in cluster size, or is it more complicated than that?
Yeah, thanks, Dr. Murray. I think the question of selecting estimand, I think, is really a discussion with the investigative team on what's going to be the scientific question they're trying to address. I think we try to operationalize this philosophy in presenting, the interpretation of these estimands by relating to what kind of questions are we asking? Are we talking about the impact at a population of individual level, or the impact to the population at a cluster level? And so it's true that the average can be different if we have really large cluster sizes and really small cluster sizes that can associate with the effect of interest within those clusters. But really, the decision to go forward with a cluster average or individual average is a scientific discussion that's really not driven by statistical model considerations. And so I wouldn't say we should always move forward with one versus another. And there could be cases where one of them is more interest and then the other, and also cases where both are of interest. So it's really a case by case discussion.
Okay, I think that's an extremely important point. I asked the question, I knew what the answer was going to be, but I wanted to give you a chance to emphasize that investigators should think about which question is most important, not what the analysis might suggest. Yeah, choose the analysis based on the question, not the question based on the analysis.
Completely agreed.
The robustness results that you showed were for linear mixed models. Do we have the same results for generalized linear mixed models with non-normal outcomes, or for generalized estimating equations with non-normal outcomes?
Right. Yeah, that's a very intriguing question that we actually wish to study very recently. And it turns out that this is really my question 3 that I want to just offer some evidence on. Not quite, and mostly because the generalized linear mixed model is relatively intractable in terms of the likelihood. It's a complex integral representation, and even though we try to look into that, but so far it's not really showing as interesting results as the linear mixed model. We try to document some of that in this recent archive paper that I show here, but in general, we found out that the elegant results of the validity of the point estimator and model-based variance only holds in linear mixed model, but not generalized linear mixed model. Even though I want to say that, even if we have a binary outcome where we clearly know that the residual error it's not going to be normally distributed, but this linear mixed and Causal model can still be a working model. You can still estimate the risk difference in a very coherent way if we believe that the structural assumption will hold, because this model is really robust to the assumptions on the random effects and the residual error terms.
Yeah, you cited the paper that we wrote in 2006 showing that model was robust to violations of the distribution assumptions, both for the random effects and for the residual error effects. We did more work that wasn't published. You can really push things very far before you get into any difficulty. And we can thank the central limit theorem. It's our friend in those cases.
Mm-hmm. And I remember that's a poster at JSM, right, Dr. Murray?
Yes.
Yeah.
Yes. You cautioned that the robust result depended on balanced data, and you could have balance or imbalance at either of 2 levels. You could have, it's pretty common in group or cluster randomized trials to have balance at a cluster level. It's uncommon to have balance at a participant level. Are you safe as long as you have balance at a cluster level, even if there is some imbalance at a participant level? And how much imbalance at a participant level is problematic?
So the proof of the results actually relies on the cluster level balance. So the assignment of AI, this variable, is at a cluster level. So we just need to really ensure we have a 1-to-1 allocation at the cluster level. The underlying balance at the individual level in a single trial realization can be substantial, but I think under the structural assumptions we have laid out, there is only a randomness the randomness of the cluster size are only exogenous in the sense that it's not depending on the outcome, the covariates or treatment. And so on average, we really are assuming away systematic imbalances at the individual level. Even though in a single trial realization, we may have imbalance at the individual level, but these assumptions we laid out really assume away that like on average.
What is your advice on how to select covariates in a cluster randomized trial? Does the number of clusters make a difference? Does it matter whether the covariates are measured at the participant level or the cluster level? Because you could have both.
Right. And that's a very relevant question in choosing models. I think in the current practice, I think we've done a variety of things, including we may just want to fit a model without covariates, or we may want to control for covariates, which we believe would remove some of the baseline imbalance, or we believe they may be prognostic. I think the exact selection of the covariates in this context is complicated and requires further study just to see if we can do better in using the data to really inform what we should control for. But I think that's a little against the pre-specification philosophy that we've been operationalizing for years in randomized trials. And so I believe if we want to write down this model in a protocol, we should think harder about what covariates will be prognostic of the outcome, and controlling for which can have a chance for improving the precision of the estimator so we can have a better power. But as to the number of covariates, I think if we adjust for individual level covariates, we have a lot more luxury than the case where we adjust for cluster level covariates, because that would be reduced in degrees of freedom at a cluster level if we only have a few number of clusters. So that's to be cautioned. But adjusting for individual level covariates are often a lot more easier in this context if we don't have a lot of clusters.
Yeah, I think that's a very important point. You want to make sure that you're going to get value from adjusting for any cluster level covariates, because you often don't have many degrees of freedom to give up.
Right. Totally.
How do we tell whether cluster size is informative?
Yeah, that's a very intriguing question that we actually wanted a study. I think part of it is to think through, is there any mechanism from a substantive perspective in the context of the trial in terms of the intervention, the population we the population we work with, and the cluster configurations we rely on in conducting the study? Like, is there any mechanism on systematic difference between the larger and smaller clusters that may eventually contribute to differences in the within cluster treatment contrast or effect? And that's a much harder question to think through. Statistically, we are thinking through possible ways to actually formally test for this in empirical data, but that's only going to be after the trial has been conducted and you get the data, right? You don't really know that before you when you plan the study. So we could find ways to reveal that evidence once we have the data, but I think it's a much harder question to think through in the stage of planning. That has to rely on a conversation between the study team to figure out, is there systematic or strong evidence on a mechanism that could lead to cluster size variation that will be informative.
Yeah, it seems like the prudent course is to plan for informative cluster size, even if it turns out it's not there,
Right.
because you can't know in advance, and you've got to write your analysis methods up in the protocol.
Right, right. I think we've seen in the collaboratory that many studies that are on a population level has really widely varying cluster sizes, ranging from a few hundred to even a few thousand. And so that's getting more common. I think it's safe not to rule out that consideration.
Yeah. Sorry, I hit the mute button. Didn't mean to do that. Another one of the assumptions that you talked about was that clusters were drawn at random from a superpopulation.
Right.
Most of the cluster randomized trials that are done are using a convenient sample of clusters.
Right.
What are your comments on that?
Yeah, I totally feel that. Part of it is the technical necessity of these assumptions to really establish the results of the models we are fitting on a daily basis. I would think that if the cluster are a biased sample from the population we intend to make inference on, there is going to be a separate conversation on what the analysis actually represent. It's really an issue of generalizability, of like, what is your target. And I would say even for a biased sample, it is possible, even though a little bit awkward, to think through a representative population that we could conceive or conceptualize the observed clusters to be a random sample from that population. But that's not going to be the population that in practice exists, right? So I feel this assumption is mostly for technical setup, so we can perform the analysis asymptotically to prove the theory. But if the clusters are drawn as a biased sample, then we have to think harder about what the analysis can refer us to. That really concerns on the expectation we are taking in this definition of the Estimands. And in addition, the same issue can happen for the within cluster sampling, right? If we have a within cluster sample that's biased, and so we may get into trouble as well.
Thank you, Dr. Lee, very much. We've run out of time, so let me turn things back to Dr. Moyer.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. You will receive an email with a link to the recording when it is available. Thank you and have a great rest of your day.
Thank you.